That's right. Thank you very much for the invitation and the introduction. I guess I don't have the lights at all. If I would have to sum up in just one word to just add to what Michael said, I think most cosmologists or theoretical astrophysicists are very much concerned with is dark matter, which is a subject that I'll talk about a little bit later. But that is definitely the expertise of most of us. So my talk title is called From Chaos to Cosmos, the History of the Universe as We Know It. I did not make a grammatical mistake by making universe capitalized. In astronomy, we call this universe with a capital U and any given generic universe with a small u. It's a small subtlety, but it's important because we actually, as we'll see it towards the end of my talk, we're actually starting to believe that there might be other universes in the cosmos, for lack of a better word, out there. So
you're doing it in the Leibniz-Institut.
That's right. Exactly. The Leibniz-Institut. There you go. It's very well fitting. So I know that Mike was teaching a history of science course, so I tried to base my what I'm trying to explain is sort of the state of the art of cosmology and of astrophysics and of our understanding of the universe, and I'm going to sort of try to cement it a little bit through the figures that have really shaped the way that we think about the universe, historical figures of great importance to our field. People who are still, even though they may have died many centuries ago, are still actually routinely brought up in conferences and debates and coffee and so forth, which I think is very, very important to always keep in mind. Lastly, I just want to say that of course it is a huge challenge to explain to a non-technical and a non-professional audience the details of astrophysics. For the most part, that's because the language that's used is, of course, mathematics, specifically differential equations, which I imagine we're not going to be able to solve in this 45 minutes. And translating those differential equations into language is really the goal of any popularizer of science. And I just want to say straight up, if anybody has if I'm not explaining something well enough, please feel absolutely free to interrupt me. I'm not a formal person at all, and I'll try to do a better job. Although there are some concepts that even I don't understand. So, all right. So, as an astronomer, I wanted to start with the picture of the sky at night. This is what you would see if you were out in the middle of the desert and you had no clouds. Sort of pseudo-familiar picture, I think. What the picture shows is actually there's many different aspects. There are many different things that are happening. There's a huge kind of fireworks that are happening in outer space. The most important being probably this big band of stars here, which is called the Milky Way. And that's our galaxy, as I'll talk to you about later. And I don't know how many people here have seen the Milky Way with their own eye. I've only seen it once or twice in my life. The Incas had such clear, actually where I saw it was in Argentina. The Incas had such clear view of the Milky Way that these black dust lanes, they're called, this black obscuration in the Milky Way were so clear to them that their constellations were actually constellations of these black dust clouds, as opposed to our constellations, which are, of course, geometric kind of representations of stars. The Incas were able to actually make constellations out of these dust clouds. Of course, you have the moon, something everybody's seen since they were born. Planets like Saturn, which do not appear to have rings or any actual feature when you see them with the naked eye. They just look like dots. But if you look through a telescope, you can see these rings. Here are two blobs that are seen in the southern hemisphere. These are called the Large and Small Magellanic Clouds. These are actually galaxies, entire galaxies that are very, very far away from us. Well, relatively speaking, they're very close, but compared to everything else in this picture, they're very far away. Something like this, comets. These were first observed, or really quite well understood by Hale, for example, and Halley. And finally, you have the rest of the night sky, just this background fuzz, which are the stars belonging to our galaxy, the Milky Way. So that's what observers, people calling themselves astronomers, would have seen since the dawn of civilization. And for many years, this was the sort of picture that people had of cosmography, let's say, cosmology, what the universe looked like. There was a flat, does this work? Yeah. There was a flat Earth with the sun being very bright, of course, going around the Earth. There's this fixed shell of stars, and then there was this idea that astronomy or scientific endeavor in general could sort of break out from this flat Earth and this shell and reveal something more profound about nature. I think the most important first discovery that astronomy made for us was to tell us that actually the Earth is not flat. That was actually an astronomical discovery. It was made by Aristophanes in the 3rd century, who was a Greek philosopher living in Egypt. And he noticed that on a specific day, it was actually the 21st of June, midsummer, that in Aswan, in this city down here, the sun was at zenith. It cast no shadow in a well. He noticed that if it was a well, the sun went directly inside of it on the 21st of June. But he knew, because he came from Alexandria, that on the 21st of June in Alexandria, actually the sun made a small angle of shadow, cast small shadows. So the only way to actually understand how the sun, assuming that the rays of the sun are parallel, could not make a shadow in Aswan, but actually create a shadow in Alexandria, was if you had this picture of a curved Earth. And he was able to use simple geometry, which we had Pythagoras was a few centuries earlier, to simply say, okay, this line, this angle here is parallel to this angle here. I know the distance from Aswan to Alexandria, and using basic geometry, you can calculate the radius of the Earth, which he did, actually, 2,300 years ago, and he did it to incredible accuracy. He did it to an accuracy which was, I think, within a few hundred kilometers of what we think it is today, thousands of kilometers. And I think this was actually the first, maybe probably the most profound statement about our own place in the universe that astronomy gave to us. It's really the first one. It really told us the Earth is not flat, it's spherical. Very contrary to perception at the time. And it actually also started a whole, let's call it a motion, where astronomy feels that its obligation is to actually tell us our place in the universe. There's so many books written in astronomy, our place in the universe, the scale of the universe. And as you'll see, most of the great astronomers have tried to understand that question. I should add that actually many years later, the radius of the Earth, or the curvature of the Earth, was actually experienced by looking at how ships come above the horizon. People notice that as a ship comes above the horizon, the first thing you see is the tip of the mast, and as it gets closer. And that was actually a nice explanation that fit in with Aristophanes' views. However, at Aristophanes' time, there's still the idea that the finger of God himself moved this celestial sphere. The Earth may not have been flat, maybe it was round, but actually there was this motion of stars, the sun and the moon, everything was moving around the Earth, pushed by God himself. This was exactly the kind of cosmography that people mentioned for many years. I probably should have had a picture of Ptolemy in my talk, but Ptolemy is vilified in astronomy, so I kind of innately can't do that. And this is the view that we had. So we had, the different shells of the Moon and Mercury, Venus. Here's the firm stars, firmamenti, these fixed stars here, and then here you're going out to more and more heavenly aspects. I should say that actually, to some extent, this is still how we see the universe. We see the universe, we look out with our telescopes, and we are actually at the center of our observations. So this is an image of a representation of many millions of galaxies that were observed with us at the center. We're right here. Just ignore this little empty part here. That's because we can't see through the disk of the Milky Way itself, so we're obscured by the disk itself. But the point is, no matter where we look in the heavens, we're obviously in the center of those observations. And the galaxies here are color-coded by how far away they are. So we're sort of, you can imagine that, when you look at things outside of our galaxy, we still think of ourselves as being in the center, even though, of course, we know that we're only in the center of our own observations. We're not in the center of the universe in any profound or meaningful way. The geocentric model was a very strong model. It lasted for many hundreds of years. And then, at some point, cracks started to appear. The first most important crack was called retrograde motion. So Mars is observed to do this little dance every so often. It doesn't just go around us like the moon. It does this it's called retrograde motion. So it moves around, then it slows down, reaches a sort of apex, and it goes backwards, and then it goes forwards again. And then people did not understand how that would be possible. People had to go back to the geocentric model of Ptolemy and try to figure it out, and people did. They found this explanation called epicycle. So the idea was that the Earth is in the center, like this. The planets go around in shells, in fixed radii, but then they're actually moving around on circles that go about those orbits. And that explains, as you can see here, so here's the Earth, This is Mars. Mars is moving around its epicycle. This is its position relative to the fixed stars. And you see it's kind of doing this little dance. Okay, fine. Let's sort of kind of trying to get the model to fit get the observations to fit the model rather than the other way around. That would have been fine had it looked like this, and you had these little epicycles where Mars was kind of bouncing around. This is actually called a cycloid in mathematics, this form here. It's actually the same shape that a point on a wheel makes as you drive. But then if you had to put all these cycloids, all these epicycles together for all the different planets, all of a sudden you had this super chaotic looking thing. It's actually quite beautiful, but it's not as simple anymore as the very, kind of obvious Ptolemaic explanation of these very, circular orbits and so forth. And it started to become a little bit complicated, a little bit hard for people to stomach. The philosophical, of course, implications of that. Because, of course, we know that Copernicus had an equally good explanation for retrograde motion. All you have to do is just put the sun at the center. So here's the sun, here's the Earth, and then this is, let's say, the planet Mars. And you see that as we fly by Mars, it executes exactly the same kind of retrograde motion. You can see that here without the movie. If this is the Earth's orbit, this is Mars' orbit, you see that as we fly by, as we come to this closest approach point here, you get this backwards motion. That was, of course, a huge leap for people to take, that actually, the sun was at the center. But Copernicus famously did it. He wrote this in his book: "Finally, we shall place the sun himself at the center of the universe. We need only to face the facts with 2 open eyes." I should add that actually Copernicus had his own epicycle, right? He had the moon on a little epicycle. That's the moon right there. That's also not so nice either. It doesn't explain everything. People accused him, okay, fine, your model's a little bit simpler, but you also have this little kind of epicyclic thing. How do you explain that? Copernicus, of course, gave us the concept of the Copernican principle that we're not in the center. But he, for all the great things that he did, he set us back a little bit. He didn't get us as far as we could have gone. Because right here you have this sphaera immobilis. He kept that aspect of it. He kept that fixed shell of stars. Of course, he had no reason not to. And of course, everything made much more sense. So we're going around the sun. And we see the sphere of immovable stars. And this is what those immovable stars look like every night if you took a long exposure of them. So this is an exposure that lasted, my guess, I would say about 3 hours, judging by the fact that each star trail is about a quarter of the circle. The entire circle is 24 hours. So there's one star that's not moving at all. That's the North Star. That's the star about which everything else moves. The whole Earth is moving, all the stars are moving around. And you always know where directly north is, because that's the one star that doesn't actually move. It's like, imagine if you had an umbrella open, you had an umbrella that's open and you're twisting the umbrella. Obviously the center of the umbrella is not moving. That's the motion that people see when they look at stars at night. And that was this idea of these kind of immovable, unshakable stars also started getting lost with Galileo. So Galileo, great discoverer of the telescope, pointed it on Jupiter, one of the most beautiful planets in the solar system, and he noticed these are real photographs of Jupiter made with a pretty poor telescope. It was the only one I could find on the internet. He noticed that you have these moons, these objects that actually are moving around Jupiter. So these are the 4 Galilean moons that were discovered. So Jupiter, all of a sudden, became a mini solar system. And you also have, now you have other epicycles around Jupiter instead of just the moon around Earth. This was also a movie here. This is a movie of the clouds of Jupiter. You can see how they move. This big red eye of Jupiter is this gigantic storm. It's a hurricane that's very long-lived, and it's many times greater than the Earth in size. Actually, Galileo was the first person to observe the let's call it spatial extent of the planets. So he was actually able to see these bands here that we can see with our telescopes. You can see them here as well, these bands. And of course, he was able to see the moon, and he was able to see Saturn's rings, and he realized for the first time that these dots are actually extended objects that are clearly seen. Jupiter is a very interesting planet with respect to our solar system. It actually has way more than the 4 Galilean moons. It has around 27 of them. This is all of them in orbit around Jupiter. Just the magenta small ones here are the classical Galilean moons. This is the, let's say, the trajectory of Jupiter on the sky. These are the orbits that those moons take around Jupiter. So if you have a good telescope, you can actually see a small solar system, a mini solar system. The 4 moons of Jupiter, these are Callisto, Io, Ganymede, and Europa, are all very, very interesting objects, specifically Io, which is this one here. Io is roughly the size of the Earth. It's quite close to Jupiter. And as a result of being close, Jupiter exerts this kind of tides on it, which means that the planet is constantly deforming. It's becoming a football shape and then a pancake, and a football shape and a pancake. And that oscillation of the planet actually drives I don't want to say a tectonic system, but you can think of it as something like a tectonic system. It actually has kind of energy that's being developed. And as a result, you have these great cracks across the surface of Io, cracks in what we think is an ice shelf, below which some people are believing that there's actually liquid water, which would be very interesting indeed. NASA sent a number of probes to Io. None have yet landed on Io, but there's an opportunity to land on Io, I think, in the near future. Jupiter is very important for our existence, actually. In 1994, we witnessed the comet Shoemaker-Levy 9 explode on Jupiter's surface. It was fantastic. I was too young to be an astronomer at that point. It blew up into 21 different fragments on entry to Jupiter's surface. It was traveling at around 200,000 kilometers per hour. It's pretty damn fast. It exploded with 600 megatons of TNT on the surface of Jupiter. That's equivalent to around 600 times the world's nuclear arsenal, 3 million Hiroshimas. I find it hard to believe that 600 times the world's arsenal is only 3 million Hiroshimas. It left these horrible bruises on the face of Jupiter that were seen for many years later. It was a fantastic event. Fantastic because it actually gave us the idea, or taught us that Jupiter is most likely, we owe our existence to Jupiter because it is what's known as the solar system vacuum cleaner. It's a huge object, just like the sun. And it diverts a lot of these comets, a lot of these meteorites that are going to be dangerous for life on Earth, are diverted to Jupiter and sucked into it and smashed into its surface. We know that the Earth has had a very, very, let's say, violent past just by looking at the moon. The moon is covered in craters, so we know that there's been a lot of bombardment on the moon. And thankfully the number of, let's say, bombardments per year has gone down significantly, mostly because of Jupiter attracting most of these things.
How do we know about the speed and the impact
of the comet on Jupiter?
Yeah.
You know it from calculating so you can actually calculate the speed. Well, you can observe the speed, I should say. You can observe it directly using a technique called the Doppler shift, which is actually very important. I can talk about it now, or I can talk about it later. The Doppler shift is the change in frequency of light, depending on whether it's approaching you or receding you. It's very similar to an ambulance that's coming by you. As the ambulance comes towards you, the pitch goes up, and as it recedes from you, the pitch goes down. And the change in that pitch tells you exactly how fast the ambulance is moving. It's actually this exact same technique that radar is used on speeding cars, for example. They shoot a radar with a specific wavelength, it bounces off the car, and it bounces off with a change in the waves that's proportional to the speed that it's going. And then the calculation of the explosion, I think, is more of something that would have to be, let's say, slightly modeled. You can see the explosion, you can actually measure how much light is coming out of it, and then you make some assumptions about the composition of the meteor, and then you can kind of calculate how big the explosion was. Yes, maybe I should go back to Jupiter.
Why didn't Jupiter function as a vacuum cleaner before? What has changed?
I think it did function as a vacuum cleaner before as well. I think before there was a much larger number of these fragments. That's maybe a more interesting question. Why is the number of meteorites in the solar system decreased? But I think that probably is related to the violence associated with the way that the solar system formed. Probably when the solar system first formed. I should add that understanding how the solar system formed is still a very large question that we don't actually know the answer to. We have some ideas, and we believe that there was a kind of a huge gas cloud that collapsed into a pancake and then sort of debris formed out of it. We use a lot of these kind of metaphors in astronomy. Cotton candy, pancake. Anyway, so at the beginning of the solar system, some 4 billion years ago, there was clearly a lot of meteorites. For example, the meteor belt, which is a sort of large ring between Mars and Jupiter, did not exist back then. So, yeah. So one of the things that Galileo did is, of course, to focus his telescope on the sun without going blind. And the first thing that he noticed was that the sun has spots. These things are called sunspots, creatively. Actually, that was a fascinating discovery. They might seem trivial, but the sun is, well, when we see the sun, well, nobody looks at it with their bare eyes, but it just looks like a featureless mass. It's so bright. But actually seeing spots made it somehow imperfect. And it showed, I think it sowed the idea that the sun is imperfect, which is a very important idea from the Copernican revolution forwards. These sunspots, this is a sunspot zoomed in, up close and personal. This is the highest resolution image ever made of a sunspot. You see that the surface of the sun has this sort of granular fabric to it, this sort of cellular fabric, and then there's this sort of kind of abyss where the sun is kind of exploding. Sunspots are associated with solar flares. These things here, these are gigantic eruptions on the surface of the sun, huge eruptions of super ionized and very, very hot gas that spew out into outer space. Actually, it can be very dangerous for life on Earth, because what happens is there's sort of volcanic eruptions, or seismic eruptions, let's say, that spew out gigantic amounts of charged particles. And if these charged particles are beamed straight at the Earth, I mean, they can wipe out satellites very easily. Satellites, communication satellites and so forth, are not shielded against these huge events because it's virtually impossible. The only way to really do it would be to use lead. Lead is, of course, very heavy, and it's very, very expensive to put lead into outer space. The cost of going into outer space, of course, is directly proportional to how much you want to put there, so putting lead is not favored. So whenever these kind of things happen, on Earth we have huge space weather stations that are focusing exactly on these things. And when there is a coronal mass ejection, when there is this kind of eruption on the surface of the sun, the trajectory of the particles is immediately calculated, and if it poses a danger, satellites are shut down. And there actually have been situations where this has made a problem. It also gives rise to the Aurora Borealis, the northern lights. Perhaps the most important discovery, well, it's hard to rank them, but one of the most important discoveries of Galileo was to see what was called the transit of Venus, which is that Venus transits the sun, because Venus is closer inner to the sun than we are. So sometimes we actually see Venus doing a mini eclipse of the sun, passing between us and the sun. I should say that he also observed the phases of Venus, just like the moon. It waxes, it wanes, and it shows exactly just like the moon different phases. But this particular observation, that Venus travels in front of the sun, has a particularly important resonance for today, because it is in this way that one of the main methods that we actually discover what are called exoplanets. Exoplanets are extrasolar planets, planets that exist outside of the solar system. And what we do is exactly the same thing. We look at a star, just like this one, and if there's a transit event, mini eclipse, we can see it in the light of the sun, the light of the star. The star light dips down as the eclipse happens. And of course, this will happen if the planet is orbiting the sun, the star. It will happen periodically, and we'll be able to get a feeling for what the year that the cyclical variation is. This is an animation. It's kind of idealized. This is just to give you an idea of what the data looks like. It's quite noisy. For example, here it would be very hard just by eye to see that the light of the sun is going down. Although here it would be much more clear. So this is a way that you can actually discover planets. And what you're actually measuring by the dip is you're measuring the ratio of the size of this thing here to the size here. So if it's 1-to-1, then you black out the entire star. The sunlight's gone entirely. If it's less, then you're measuring the ratio of the relative sizes. There are other methods to discover extrasolar planets. One is called the radial velocity method. So what I was explaining before with the Doppler shift can be used as well to understand whether a planet is moving away from us or towards us. So when you have a planet orbiting a star, actually this star also orbits around. They actually orbit what's called the center of mass of the two objects. They're both orbiting around this little plus sign. Actually, that's the same for our solar-centric solar system as well. The sun also bobs in response to Jupiter's pull on it. So the sun is actually not just perfectly in the center of the system. The sun is also actually moving towards Jupiter, exactly like this. If the motion is fast enough, and this star here is really moving back and forth with respect to the line of sight very, very quickly, or fast enough, let's say, then you can actually quite easily see the change in light. As it goes further away, the light's red. As it comes closer, it's blue, red, blue, red, blue. And you can infer then that there's a star pulling on it, or at least something is pulling on it. That's called the radial velocity method to find exoplanets. The best way of finding exoplanets is direct imaging. So you take a photograph of two planets, or that's right here. So it's a very difficult thing to do. It's virtually impossible. Why is it virtually impossible? Planets don't shine. Planets reflect light. They don't shine on their own. The star that the planet is orbiting is very bright. It washes it out. So the only hope that you can do is you get a planet that's really far away from the star, so it's not wiped out by the sun of the light of the star. But then the farther away you get, the less light from the star is incident on that planet, so the harder it is to see. It's a very difficult method. There's literally, I think, a handful of these things, direct imaging, but it's by far the most exciting. I just want to, so talking about Galileo and his discovery of the moons of Jupiter, made me want to digress a little bit and talk about finding exoplanets. One of the most exciting things, which is just happening right now in this field, is actually searching for the signature of life in exoplanets. You might think this is science fiction, but it's actually not. When you have a transit event like this, where you have a star and you have a planet that's moving in front of it, so all the light of the star that's hitting the planet is going to get blocked out. This light's not going to get blocked out. But what about this light here that's passing just in that tiny little atmospheric region, that's passing through the atmosphere of the planet and continuing? Well, the composition of that atmosphere is going to leave a signature on that light. We're going to see, for example, if there's oxygen, if there's methane, if there's other, not only organic molecules, but also inorganic molecules. We can actually begin to probe the composition of exoplanetary atmospheres, which is an idea that was completely far-fetched. Even 5 years ago, nobody thought this was possible. And the reason nobody thought this was possible is because the star itself appears as a point in the sky. The planet appears as an even smaller point. What are the chances that you can actually measure light coming, in this tiny little region? It's very, very hard to imagine. However, our telescopes are advanced enough. We have actually very good resolution, and we can see this happening. I wanted to mention that, the goal, of course, is to discover some kind of life on another planet. In this field, there's a concept of the habitable zone, which is the distance that a planet must exist from its star such that liquid water can exist on the planet. So if it's too close, like Mercury is, for example, there's no liquid water, the sun is too hot, and if it's too far away, it's iced. So there's this idea that there exists this kind of habitable zone. So the goal in this field is to search for planets that have the size of Earth, that have in their atmosphere telltale signatures of life, and that are far enough away, just close enough and just far enough, just in this perfect balance from their star. And the hope is, of course, that the star is something similar to our star, not too hot, not a dim star, and not a too bright of a star. You might say that that's a lot of requirements, but there's a lot of options. This is kind of an artist rendering of what we think the universe might look like if we actually had loads of planets orbiting every star. This is a very nice plot that shows the year here and the number of exoplanets that have been discovered. This is 2014 right here. So you can see that we're living in a golden age of exoplanetary discovery. It's something absolutely fascinating to witness. Just 3 years ago, when I started my PhD, there were just 9 planets. And then it actually went to 8 because they got rid of Pluto. It actually went down. And then, some planet here was discovered, some planet there was discovered. Some people said, oh, maybe that's the planet, maybe it's something else, I don't know. And then really in the past 4 or 5 years, this thing has just shot up. This is mostly due to just one satellite called the Keplers satellite, which has discovered a lot of these things. I couldn't help but, on the topic of life on Earth, mention Drake's equation. This is not really my field of, yes? Was that a question? No. This is not really my field of research, but it's something that all astronomers are thinking about. So the question that Drake asked, he was an astronomer from the 60s, is how many extraterrestrial life forms are there? And the way that you calculate that is you simply say, okay, so the number of extraterrestrial life, so the number of stars in the Milky Way, times the fraction of stars with planets, times the average number of planets per star, fraction of planets in the habitable zone, fraction of those that can have life. You can add as many as you want, actually. And then you adjust this with the scientific method. So how many stars are there in the Milky Way? 100 billion. That's a big number. How many of them actually have planets? Well, we're starting to believe that this is approaching 1. This is almost all of them. It's possible that all of them are planets. We don't know. Anyways, I don't want to go through all the different permutations, but the optimistic view is that there's around 100 million planets with life in the Milky Way alone, and the skeptical view is that there's 10,000. And that's just in our galaxy, and of course there's billions of galaxies. This is actually a serious field. You know, in 1996, I think it was, there was a Mars meteorite found, and this object here was announced by President Clinton as possibly being a fossil from outer space, right here. And this is actually, this debate of this Mars meteorite is still raging. Well, raging 4 years ago at least, there was a claim that on the surface of it was this biomorph thing. And it's not unthinkable, actually, that there could actually be life on meteorites. Actually, one of the most convincing theories that was developed by Sir Fred Hoyle, who was one of the most important astronomers of the 50s, was an idea called Panspermia, which is that actually life did not originate on Earth, but actually came to Earth from outer space in the form of living on comets. People dismissed Fred. I mean, Fred Hoyle was one of the greatest astronomers ever, but they dismissed this theory. They said it's impossible. No life can survive outer space. You need to have temperate conditions. You need to have water. You need to have, et cetera, et cetera. But then we started discovering things that are called extremophiles. Extremophiles are organisms that live in very hostile events. For example, there are organisms that live deep at the bottom of the sea, right outside of sulfuric vents, places that we would consider to be completely poisonous and toxic, that would be absolutely impossible. The pressures of the waters are huge, and it's toxic, etc. And actually, there are organisms that live there. Furthermore, there are these really bizarre creatures called tardigrades. They look like bears that actually can survive exposure to deep space. So these are animals. They're actually not microscopic. They're actually macroscopic. You can see them. They're very small. They're like mites or like lice, kind of tiny. There's a NASA and a European Space Agency experiment called EXPOSE on the ISS, where these things are actually exposed to deep space without oxygen, the harsh realities of a vacuum, and they survive. They survive exposure. So it's not unthinkable that this kind of panspermia idea is real, at least for some of us. Of course, there's no evidence. There's no evidence for it. It's just a theory. All right, let me try to go back into my historical explanation. We used to believe that the Earth was in the center of the universe. These pieces of evidence: the moons around Jupiter, the retrograde orbits, sunspots and their variation, the fact that the sun is actually dynamic and not eternal, transit of Mercury and Venus, and the phases of Venus really pushed us from the Earth being in the center of the universe to the sun being in the center. And that was all fine and dandy. Until Tycho Brahe, who was a Danish astronomer, he was a very fortunate man. He was fortunate because the King of Denmark gave him this island here called Ven, I think, V-E-N. It's right between Denmark and Sweden. He gave him the entire island, so all the taxes from the island are going to go to your observatory. So poor islanders got completely impoverished by his attempt to make the greatest catalog of stars ever made. That was when science funding was really good. He was the last of one of the great astronomers who didn't have telescopes. And he noticed in 1573 a nova star. A nova star is a new star. So that's this one right here. Very, very bright new star. That's a little bit perplexing. The fixed stars are fixed. They don't move with relationship to each other. There's not that much happening there. Anything that's happening, any kind of comet or phases of Venus, is happening inside of this fixed, immovable sphere. Okay, fine. So maybe this nova that he saw, maybe it's something happening in the Earth's atmosphere. Maybe it's something happening in the solar system. How can we prove it? How can we disprove it? How can we falsify that claim? So anything happening within the solar system shows an effect called parallax. Parallax is, what's the best way? This is a video that shows how it works. Parallax is the movement of an object with respect to something behind it when you're moving. So for example, when the Earth is in June and you see the stars, so these are the fixed stars here. Imagine there's an object right there. When the Earth is in June, it appears closer to these two here, in this position here. And by the time we're 6 months later in December, it actually looks like it's close to this star, like that. So the star itself is moving with respect to the background stars as the Earth is going around its orbit. So he tried to calculate a parallax to this nova, and he couldn't do it. This nova did not move with respect to the background stars. And that's because if you wanted to calculate this parallax, if you wanted to see how much a star would move Here's an idea of how difficult it is to measure these things. The closest star is Proxima Centauri. It's around 4 light years away. The parallax of Proxima Centauri is around 0.7 of an arc second. You guys aren't astronomers. You don't know what that means. It's around 1/10,000th of a degree. That still means nothing. This is half a degree. The moon is half a degree. So to give you an idea of how much of parallax that star shows, it shows around 1,000th of the moon. So imagine how big the moon is, and measuring the motion of a star 1,000th the size of the face of the moon. Obviously completely impossible without a telescope. Even today, we can only do these parallax measurements out to about 300 light years with the most state-of-the-art telescopes. So the fact that this nova that Tycho Brahe saw did not show any parallax, did not show any movement with respect to the fixed stars, really made people realize that maybe there is something actually dynamic happening in this fixed star, in this fixed stars. So what exactly did he see? What is a nova? A nova is this new star. It's a star that appears that did not exist before. I'm going to try to explain this briefly with a cartoon. Stars are shining because they have got thermonuclear explosions in their center. 2 hydrogen atoms are fusing into helium, exactly what happens in a nuclear bomb, and they release energy. And that energy is just like Atlas. It's holding up the outer parts of the star. So the part that the star wants to fall in, there's gravity trying to attract it, and these explosions are keeping it aloft. At some point, the fuel runs out, and the star collapses and explodes in a cataclysmic event. These are actually, some of these are photographs, and then this is kind of transitioning to animation. Novas are amazing objects. They're one star that appears bright as billions of stars. The magnitude of the shine of the nova is so huge. It's imagine you had 1 billion people clapping and one person clapping louder than all of them. It's absolutely amazing. This is, for example, the nova star in this galaxy. And in the center here, you have billions of stars, and it's just as bright. This is a photograph of a nova star. This is a very dynamic picture. You can really see the explosion happening. These are hot ionized gas driven from the internal explosion that are being funneled. Actually, it's possible that many of these novas are actually pointing one way or the other. Here's another image of a supernova. You can also see the ionized gas. These are optical images, so these are images that you could take with your own telescope if you had one. You don't actually need to have such strong telescopes to see these kind of events. Unfortunately, novas don't happen that often anymore. They happen around once per galaxy per year or per century. It's not a lot. It's very little. In our galaxy, they haven't happened since 1987. They used to happen a lot more. When you're looking at the past universe, you see novas all the time. But when you're looking at our galaxy, it's like not that often, unfortunately. This is what most novas look like. They're not so spectacular. Like I said, most novas are seen in other galaxies, not in our own. So you have this kind of image of this kind of field. You zoom in onto this little galaxy. Here's a very kind of poorly resolved galaxy. And a few days later, you see that there's a little dot right there. And that's what the nova looks like. Actually, Kepler also had a supernova that he discovered in 1604. It's this N right there in 1604. It's called Kepler's supernova. It's nice. He told us exactly where it is. We can photograph it. This is what it looks like today. And we know that 400 years ago, it didn't exist at all. So we can actually try to understand how these supernovas are working. But Kepler's greatest contribution was definitely not novas. It was Kepler's third law. Now, I didn't want to put any equations in, but I figured I had to put one equation in, which is the relationship between how far away a planet is and how quickly it moves. So this is an animation of what the solar system looks like. And you see that Mercury goes really, really fast around the center, whereas Mars travels much slower. If you plot the orbital speed versus the distance, it drops like that. It's actually the first time, this is the first time that a mathematical equation was actually applied to astronomy. Never before had that been done. So actually you could say that he was the first astrophysicist. He had no idea why the orbital speed was proportional to the distance. But Newton did. And I'm not going to get into the equations, but I put one in, so I might as well just go through all of them. All right, who wants to start?
You should ask the students.
Yeah, exactly. All right, so Newton, in his Principia, he made this famous F equals ma, and you go through some circus, and you actually get exactly the equation that Kepler came up with. And what's nice about the equation, actually, instead of just being proportional, Kepler just found it proportional, actually Newton found that it depends on the mass of the star in the center, the mass of the star. So it actually means that you can use the relationship between the speed and the distance to calculate the mass that's inside. This is actually how we weigh planets. How do we know how massive the Earth is? We know how massive it is because we see the moon and we know how far away it is and how quickly it's moving, and we can estimate the mass from this equation right here. We can estimate the mass of the sun in exactly the same way. We can estimate the mass of Jupiter in the same way. Everything that we know, the moons of Jupiter, the rings of Saturn, the solar system, the moon, follows this law. This t squared equals a cubed. Except for galaxies. So when we look at galaxies, we would expect them to, this curve here, what you're always seeing here, this is sort of Keplerian motion, what you call. But what we see actually, so this is the speed of a star versus the distance from the center of the galaxy, is that these things are flat. So the outer parts of the galaxy are spinning really, really fast. We have really no idea why that is. Well, we have two ideas. There's two possibilities. Why are galaxies spinning so fast? Either F is not equals to ma, Kepler's law is wrong, and Einstein, of course, is wrong, and we need a completely new paradigm and a completely new understanding of gravity. That would be great, and there are many, many Nobel Prizes waiting for whoever figures that one out. But nobody has. The only other option is to keep our theory of gravity from Einstein, and to add something called dark matter, which is a halo. It's a region outside of the galaxy that's way, way larger than the galaxy, which is invisible, except through its gravitational effect on the stars. So it's like this galaxy is no longer sitting in empty space, it's actually sitting in a very, very deep, it's called potential well, very, very deep, dense area. All right, I realize that I have taken more time than I wanted to getting here, so I think I'm going to skip Giordano Bruno and his publish and perish. No? Okay. All right, well, publish and perish, right? That's what Giordano Bruno said, famously. He took Copernicus' idea of the immovable spheres. He combined them with Galileo's amazing pictures of the moon. This is the first picture of the moon ever made. First realistic picture of the moon ever made, right here, from 1609, from Galileo. There were watercolors, too. Absolutely amazing. And he said, well, I don't know what he said because his works are in Latin and I can't read them, but the charges against him are published in English. He said the world was eternal and that there existed thousands of worlds and that all the stars could be seen were worlds. And that was his count 5 against Giordano Bruno. He was burned at the stake in Campo di Fiori in Rome. And I think he's another first. So Kepler might have been the first astrophysicist. He was the first science martyr, the first person who really died for the ideas of astronomy. His ideas that all the stars were worlds were taken very seriously by Herschel. Herschel was a great English astronomer. He was a very rich man, had his huge telescope for the time. And he went on a campaign to map all the nebulas. So they knew at that time that there was two different types of objects in outer space. There was point particles that are stars, and there were extended objects that were nebula. I'll show some pictures of them in a minute. So he wanted to map where are all of these nebula. And he did some basic kind of assumptions about how to get the distance. In astronomy, distance is a very hard thing to measure. For example, like the sun and the moon, they have exactly the same sky, the same size in the sky. One is gigantic and far away, one is tiny and very close. So I don't know how, it must have driven those people crazy that they couldn't have figured it out before. But astronomy has always been, the challenge of astronomy has always been, and still is, determining distances to objects. And there's different ways you can do it. I don't want to go into too much detail. Herschel had his own method. And this was the picture that he made of the Milky Way galaxy, of all the nebula in the Milky Way. Actually, it was wrong. Well, we'll see later that it was wrong. But you see that it's kind of this weird shape here. And he put us off-center. It's quite nice, actually, that we're not in the center. He also mapped some stars. There are also stars in here as well. This is actually a modern view of what he mapped. I think in red are the nebula, and in green are the stars, I believe. These are the kind of objects that he was looking at. This is a supernova remnant. This is what's left over behind a supernova. This right here is called the Tarantula Nebula. It's a star-forming furnace in the universe. It's gigantic. Many stars are being born in the center of this object. This is what's called an open cluster of stars. This has got around 1,000 stars here that are being born, mostly here. They're enshrouded by this gigantic gas cloud. And this, of course, is a spiral galaxy. Now, one of these things is just not like the other. These three things are very close. This thing is very far. Now, before I go on to go on to that, let me just add that, so we had the movement from the Earth being in the center to the Sun being at the center. I think these ideas, these observations of nebula, star clusters, supernova, and spiral nebula really made the Sun become just another star, as Giordano Bruno said. And all of a sudden our galaxy and the entirety of our universe became just our galaxy. So what is a galaxy? This isn't the fun part of the talk, for me at least. Galaxies are the most beautiful objects that there are in the heavens. These are spiral galaxies. This one here is called the Sombrero Galaxy. We give some creative names. Well, you should be happy. This one here is like M82 or something. It's got some telephone numbers and adds the name. Actually, you see different types of galaxies. Here you see spiral arms. You see this blacked out region is dust. Actually, when I say dust, I mean dust. I mean just exactly what you think of dust. No, I'm not joking. It's exactly the same kind of garbage that prevents you from seeing the interesting stuff. This galaxy has a bar in the center, right down the middle, and you have two spiral arms around it. This one here has a huge outflow from the center of the galaxy. Inside the galaxy, there's probably a black hole which is exploding or something, or eating another star, and it's emitting these red flares around it. You actually see the presence of dust, these black things, in almost all spiral galaxies. It's almost a mandatory aspect of a spiral galaxy. But galaxies are not only spiral, they're also blobs, elliptical galaxies, that are relatively featureless, like this one, or this one is completely featureless. There are billions of stars here, and they're so far away that you can't resolve them, so they just look like a fuzz. Sometimes you get some dust in the middle of an elliptical galaxy. This one here is a jet. This right here is a jet. It's a jet of very hot air, hot gas. Elliptical galaxies are much bigger than spiral galaxies. Galaxies can be classified in this tuning fork diagram. So you have elliptical galaxies here that are classified by their shape. As you get closer and move this way, they get squashed. And then you split and you have spiral galaxies and you have these barred spiral galaxies. Almost all galaxies can fit into one of these two categories, elliptical or normal, or spiral. I mean, of course, there are some that don't, but most of them do. Okay, let me just see if I can go through this quickly. Actually, Hubble, one of the greatest astronomers in the 20th century, was the first person to suggest this tuning fork diagram. This is his original picture. And it was noticed at that point, this is now the beginning of the 20th century, that these spiral galaxies and elliptical galaxies are actually everywhere on the sky. So this is what it looks like. This is like a map of the Earth. I don't know if you've ever seen a map of the Earth in this projection. This kind of ellipse. This is the same kind of thing, but of the sky. So you take the entire sphere of the sky, you project it onto a two-dimensional surface, and you get this kind of ellipse. And you see that there's actually these galaxies everywhere.
So what's in the center?
In the center is our Milky Way. This is the Milky Way itself. So you have the band of the light of the Milky Way, which is then put into this projection as the equator of the Earth, for example. It's right in the middle. The Milky Way has this bulge, and then it's got these dust lanes, and it sort of thins out as you get to the outskirts of it. In the beginning of the 20th century, there was this famous, most important of the great debates of astronomy on the scale of the universe. It appeared in these conference proceedings here. William Ellery Hale lectures, the discussion, the scale of the universe, between Shapley, who was a great astronomer but got the debate wrong, and Curtis, who was far less known but was actually right. And the debate was, are these spiral nebulae, are they inside of our galaxy or are they outside of our galaxy? The arguments that Shapley said were, given the size of one of these spiral nebulae, and knowing something about its distance, and knowing something about its size, so you measure the size in the sky, and you say, let's assume it's as big as the Milky Way. How far away must it be to be that small? It would have to be, well, astronomically far away, greater than 1 million light years away. That's okay, actually. For him, it wasn't okay, but for him, that was an argument against it. Also, here's a really annoying aspect of the puzzle. This horrible person, Van Manen, actually claimed that he measured a galaxy spinning. And at these distances, there's no way that you could possibly measure that. It would have to be spinning faster than the speed of light. So that was a very strong argument against it. Turns out the measurement was completely wrong. Nobody's ever observed a galaxy spinning that way, like physically rotating. Curtis said no. He said that there's more Nova stars in one small part of the sky than there are in the entire Milky Way. And he said that doesn't make sense unless it's its own galaxy and it has its own novas. Also, he noticed that there was dust lanes, which we also see in the Milky Way. Eventually it was settled by Hubble, who found that the universe was expanding. So he measured the distances to these galaxies and their velocity, and he saw that, wow, they're proportional. The further a galaxy is, the faster it's moving away from us. This is probably the biggest discovery in astronomy since discovering that the Earth wasn't flat. This was the first time that we actually realized there is no immovable sphere. The immovable sphere of stars is actually a huge universe that's expanding, and the distances are absolutely beyond comprehension for mere mortals, including myself. Extragalactic nebula moved our galaxy to just become one of a huge number of galaxies in the universe. A gigantic number. Okay, I'm going to... Yes?
Can I just ask, what year did Hubble?
That was 1922 maybe.
And are there many antecedents to that discovery, or did it really just come out of the blue? So to say, out of the...
It didn't come out of the blue at all. In fact, a Catholic priest named Lemaitre, can't pronounce his name, predicted it from Einstein's theory of gravity. So he took Einstein's theory of general relativity, and he made some assumptions for some of this, how the solution for the entire universe would work, and he found a very unstable universe, one that would either collapse or expand. Actually, Einstein knew about this, and Einstein tried to fix his equations with a term called the cosmological constant that prevented the universe from expanding or collapsing. He afterwards regretted that, and he famously called it my greatest blunder to add that term once that we discovered the expansion of the universe. But Lemaitre not only predicted it from Einstein's equations, but also calculated how fast it should be expanding, and he was pretty close actually to the real thing. But the problem was, I had this in my lecture before, but I took it out. The problem was, as I said, getting the distances to these galaxies was very hard, and we had to wait for a great forgotten woman of science, as most women usually are. Their usually work is ignored. Henrietta Leavitt, who was a PhD student at Harvard, was the person who came up with the concept of how we can actually measure distances to galaxies, basically using something like supernova stars. She, of course, got no credit for her work, but her work is what led Hubble to his discovery. So we see all these galaxies moving away from us, but of course we can't be at the center because Copernicus told us we're not at the center. So how is that possible? I mean, people immediately said, how is it possible that everything's moving away from us, but we're not at the center? So the best way to explain that is using the metaphor of bread, and imagine you have like raisins inside the bread, and then you put it in the oven and the whole bread expands, and from every raisin's perspective, every other raisin's moved away from it. It's a metaphor that works, except for I don't want to confuse you with dimensionality, but... Okay, I got to finish up here because I'm over the time that I allocated to myself. I just, maybe in the last few slides, how many slides do I have? Not that many. What is the fate of the universe? The universe is expanding, and of course galaxies are pulling on each other due to their gravity, and we see galaxies colliding. This is what it looks like when two galaxies collide. This is what it looks like. These are photographs here of colliding galaxies. This is a simulation, the kind of stuff that I'm working on. You can see these things colliding. This is called the mice. Galaxies. In fact, we're going to collide with our closest neighbor, Andromeda. This is what the Milky Way looks like today. In around 3 billion years, Andromeda Galaxy is going to have closest approach, it's called, first impact. And then in 6 billion years, this is what the sky is going to look like. It's going to be a completely different night sky. There's going to be 10 times more stars in the sky than there are tonight. Don't worry, don't take out an insurance. The chance that two stars collide is very, very small. It's actually a nice experiment that we give first-year students. Calculate how many stellar collisions are there when Milky Way collides with Andromeda, and the answer is around one collision out of 300 billion stars. So it's not that much of a problem. The future of the universe depends on how much matter there is in the universe. This is what a collapsing universe looks like. So you have a big bang. There's so much matter in the universe that it forces a gravitational collapse, and you have something called the Big Crunch. You could have just enough matter in the universe to balance the expansion. That's called the critical universe. Because in this scenario, the galaxies expand. They get slower. They move slower and slower away from each other until they're not moving away from each other anymore. This is the universe that we thought that we lived in until very recently. This is what I was taught in university. The Nobel Prize in 2000 and 12, I think, was given to the discovery that the acceleration of the universe is actually accelerating. The speed with which the expansion is happening is getting larger. How do you do that? I mean, you need to calculate, you need to count how many galaxies there are in the universe. How do you count how many galaxies there are in the universe? It's a very difficult thing to do. The Hubble Space Telescope had to go. They stared at a tiny little patch of sky, this little black square right here called the XDF, the Extreme Deep Field. There was already an ultra deep field and a deep field. So creative naming, I tell you. And they came up with this picture here. In this picture, every dot is a galaxy. Every dot in this picture harbors hundreds of billions of stars. Then you count how many galaxies there are in here. It's around 10,000. You multiply it by this ratio between this little square and the entire sky, and you get something like 300 billion galaxies in the observable universe. But of course, there's many that we can't see. This is what the distribution of galaxies actually looks like on the greatest scales. So these are billions of light years. These cones are because we're looking in like a cone, like an angle. And this one looks at every dot here is a galaxy. And I should caution you, the reason that there's not that many dots here and here is not because they're not galaxies, but because the galaxies are so far away, they're so dim, our telescopes can't pick them up. This is the fabric of the universe on the greatest scales. These are billions of light years across. And you see features. You see a pattern. You see something which begs to be described mathematically. What's going on? For example, you see huge contrast. You see this region here, which is devoid, it's empty. There's like one galaxy in a huge volume. And you see this region here, which is relatively speaking packed. You know, thousands and thousands of galaxies in a very, very small volume. I mean, very, very small is relative, of course, but it's still huge. But the point is that the density of galaxies, the number of galaxies, is much, much higher. So how did this originate? And this comes when Michael wanted me to actually explain how the new discoveries from Bicep 2 and inflation. We think the universe started out very homogeneous, very, very equal in all places, but with very, very small clumps that then evolved and got bigger and bigger. So let me show you a movie. I'm going way over the time. So this is a movie that is supposed to show how the universe evolves. So you get these clumping effects that then grow bigger and bigger and bigger. It's like gravity is the ultimate capitalistic force. The rich get richer, the poor get poorer. Regions like this grow into huge clumps, whereas regions like this, for example, or here, they get emptied out of material. And the real question is then, what seeded these initial tiny little clumps in the universe? I should say this is exactly my background. It's known as the cosmic web. And the seeding comes from inflation, comes from a period at the very beginning of the universe, where you have this kind of universe was kind of completely flat, and you have this random noise of fluctuations that happen in this completely flat space that give rise to these clumps of material that are then the seeds for the whole story.
What is this noise?
So in quantum mechanics, you have the uncertainty principle, which tells you that there is no such thing as, let me see how to properly explain this. In the early universe, you had nothing. However, nothing in quantum mechanics, the uncertainty principle tells you that you can never have nothing. That you always have a probability that something will spring into random existence out of nothing. So basically, imagine you had a vacuum chamber. Imagine you had a little room that was completely empty of everything. Quantum mechanics tells us that at a given instant, you could have an atom popping into existence out of nowhere that could exist for a very short period of time, and then again, gone. It disappears. And that's because, well, the uncertainty principle, the way Heisenberg phrased it, is usually got to do with position and velocity, but it can also be cast as energy and time. You can borrow energy for a certain amount of time, and then you have to give it back. Now, what happened at the beginning of the universe is that this effect happened. Energy was taken out of nowhere and then given back, and taken out of nowhere and given back. And there was these kind of random fluctuations that happened. And at some point, we don't know why, these random fluctuations started expanding. And all of a sudden, you had regions that had borrowed something from this empty space, but were not able to give it back because the universe expanded to huge size. That's the theory of inflation. And actually there's proof of it now. There's proof of it from the CMB, the cosmic microwave background radiation, and there's proof of it from BICEP 2, this experiment that made a huge splash about a month ago. Would definitely lead to Nobel Prizes. There's no doubt about it. Let me just say that inflation, this is the last idea that I wanted to mention. The concept of inflation solves one of the most curious problems of mathematics, of the universe, which is something called the anthropic principle. So people ask the question, why is the charge of the electron exactly what it is? Why is the mass of the proton? What these fundamental constants that exist. If the universe was any different, if they were any different, the universe would look completely different. So Martin Rees, the famous astronomer, showed that there was actually 6 numbers. I don't want to go into them, but they're fundamental constants. That if they were even a tiny bit different, would not allow the universe to be existent. It would not allow stellar fusion. Would not allow the speed of light, etc., etc. Not allow human beings. So people have often answered it by saying, "Well, they are the way they are because if they weren't, then we would not be here." And then the question is moot. And that's a very uncomfortable answer. It's kind of a frustrating answer. It's true. I mean, if there was no wave to make molecules, then we wouldn't exist. Inflation predicts that in these fluctuations, there's actually fluctuations of these values as well. And that actually, and this is for me the hardest thing to understand about the theory, there's actually multiple universes, each with a different combination of these 6 numbers that exist outside of our universe. There are universes that have no light. There are universes that have no atoms. There's universes that have completely different values for these constants. And I guess the reason I wanted to stop here was because we've gone from the Earth to the Sun being important, from the Sun to the galaxy being important, from the galaxy to at least our universe. And what we've learned last month is actually our entire universe might just be one of a multiverse, of an infinite number of universes, each one completely different. I don't know. I think Copernicus has to stop there. I don't think we can get any further away by saying our entire universe is like not important. I mean, I thought at least our universe should be important, but Okay, I'll stop there.